All right, so we're going to start. Thanks so much for coming. This is the contributor session 5C, Advancing T&E of Emerging and Prevalent Technologies and Improving the Quality of Test and Evaluation. One kind of update is, unfortunately, Mark Archwell was not able to make it, but you have three lovely speakers here and a bit more time with them, so it might be a good silver lining. And then for the folks who are on virtual, you can definitely ping your questions, but what I'm going to do is I'm going to wait until the end to ask those questions, just to kind of keep the momentum of the talks going. Okay, all right, I think that is pretty much it. All right, so I'm going to introduce our first speaker. Let me just pull it up. I use my phone. I'm a millennial. What can I say?
Appreciate your honesty.
Also, I take positive affirmations. Please tell to my mom. Right. So I'm excited to introduce Dr. Brooke Corbett. She is a research staff member at the Institute for Defense Analyses. She has worked on a broad range of programs within IDA's Operational Evaluation Division, including live fire, test and evaluation, survivability, and lethality evaluation for the U.S. Army, Air Force, USSOCOM, Navy, and Space Force programs. Dr. Corbett is developing subject matter expertise to support survivability and lethality evaluations of U.S. directed energy weapon systems on DOT&E oversight and supports survivability and risk analyses for select NASA engineering and safety center programs. She earned a PhD in material science engineering from the University of Denver in 2008 with research focused on survivability and risk assessments of hypervelocity impact damage response to the International Space Station's Meteoroid orbital debris shielding at elevated temperatures. So basically, she's quite a smart cookie. She earned a master's in Physics and Astronomy from the University of Denver in 2001, with research focused on middle atmospheric long-wave infrared measurements and line-by-line radiative transfer model predictions of water vapor and carbon dioxide in polar regions. She earned a bachelor's in physics from Moyne College with project work focused on optics and the manual creation of a parabolic primary mirror for a Dobsonian telescope. So enjoy the talk.
Hi all, I'm really glad to be here today. Hope you all can hear me. And those of you in Zoom land, when I was listening earlier yesterday and today, I noticed when the speaker stepped away from the microphone, I couldn't hear. So I'm going to stick to the podium if I can help it. Not how I usually brief. I like to walk around a little bit. But I'd like to thank first my closest colleagues who supported this work, Dr. Joel Williamson and Bob Stellingwerf, who provided the data for the investigation I'm about to discuss with you today. And our research sponsor was the NASA Engineering Safety Center. Many thanks to Dr. Mike Squire. This was a really fun project that harkened back to, as was just introduced, my PhD days in hypervelocity impact studies. And this project, you're going to hear TPS a lot, you're going to hear SPHC a lot, and you're going to hear MSR a fair amount. Just remember that TPS is thermal protection systems. SPHC is reference to the smooth particle hydrodynamics code. And MSR, really not MSRM, is the Mars sample return. That's what I'm going to refer to the vehicle and the mission. But in support of a joint venture between NASA and ESA, they had a very lofty goal called the campaign called the Mars Sample Return Mission, where IDA participated in a small part, but very important part, conducting a series of meteoroid impact damage simulations using two types of spacecraft composite protective structures that I'll show you in subsequent slides, using the smooth particle hydrodynamics code. And what is SPHC? Some of you who might have attended some of the talks the other day that featured SPHC, it's a specially designed hydrocode. It's a Lagrangian, a gridless Lagrangian hydrodynamic computational technique that was devised at Los Alamos, not San Diego, Los Alamos National Labs, I think back in the 90s. And Bob Stellingwerff, who produced these simulations, was a creator of this code. This particular code is specially designed to accommodate large deformations, large transformation of materials, large void fractions. That's about as physical as I'm going to get with some of that language, because I know the audience is not very technical as far as the hypervelocity impact area, but this is basically an ideal candidate for this type of simulation. And so the particle portion of SPHC, for those that are familiar with hydrocodes and meshing structures, the particle is analogous to a mesh point in a typical traditional hydrocode. So in this effort, we consider the potential effects of meteoritic and non-meteoritic particle impacts, and I'll describe what those are after, into the two types of shielding, which are the shielded four-body thermal protection systems for an extreme entry environment, and an unshielded aft body thermal protection system that's similar to the material that protected the space shuttle external tank way back in the day. Unfortunately, resource constraints and NASA shifting priorities as far as what they wanted to do with the program and how they wanted to protect this portion of the mission really limited funding and then the amount of simulations that could be produced. However, the results were adequate, and we felt it was important to publish these, because this may serve as a likely solution for a follow-on to the MSR campaign. And what do I mean by that? I'll talk about that in a minute. So this effort, you'll hear me talk a lot about a prior research or a prior study conducted by Williamson et al. He was my co-author on this paper, but he was a primary author on the first part, I would say, of this study that was really published back in 2022 that did the similar methodology using SPHC to simulate the meteoroid damage into a dual wall aluminum TPS. Now, that's what NASA changed their mind. For a variety of reasons, given what the analysis showed, they decided to go away from a dual wall TPS, aluminum TPS, and go towards a composite sandwich type of a garage structure over a TPS. And I'll get into that in the subsequent slides. You'll see here that there's a screenshot of the proceedings or the paper where the first paper was published. As an officer of the Hypervelocity Impact Society, I'm just going to give a couple-second plug that the first portion of this was presented at Hypervelocity Impact Society Symposium 2022 in Alexandria. The second portion that I'm here to talk to you about today was presented in Tsukuba, Japan at the HVIS 2024, and the proceedings are in process right now. And 2026 is coming up in Monterey, California. So if you're interested in the types of not only planetary impact, not only meteoroid impact, but there's a broad range of topics that touch the national labs, the DOD, and academia. So check it out if interested. Okay, so here we get into the fun stuff. I wish I had enough time to show you a video of a very lofty goal that NASA had with this whole campaign. It was a multi-phase approach that it was pretty incredible. It was supposed to take a couple of decades, and unfortunately NASA's budget was orders of magnitude off from where the writing on the wall was projecting the budget for this campaign was going to go. So that really led to the demise, very high risk with not being able to complete this. What you see here is and the DoD, what they would consider like an OV1. It's an operational depiction showing the Mars sample return campaign when the concept was slated to use the orbiter here, this whole portion, to return the samples that were collected by the Perseverance rover that was already up there to the Earth. The goal was to ensure safe re-entry of these Martian regolith, or fancy word for soil samples, into the Earth's atmosphere and reduce the risk that the shield, the capture and containment system that was holding the samples would not break open and release potentially biohazardous Martian materials into the Earth's atmosphere. And so there was a real fear that that would happen. You know, I know that there are movies that harken back to that, but that was a driver for NASA's design goal of this program being a 1 in a million chance that the sample would be exposed to the Earth's atmosphere upon re-entry. The actual calculated risk, I'm told by my co-author, turned out to be less than a 1 in 500,000 chance of the TPS failing on re-entry, just for situational awareness. As I alluded to, the program was canceled last year after NASA determined it was way too costly and time-consuming. However, the current analyses will indeed form shield designs that are likely to be used on a follow-on program or other similar programs. Importantly, IDA's focus in this program was on the hypervelocity test and analysis portion. And so you see this part here. This is the Earth entry system with the thermal protection system covering it. And look at this cutaway. And then here you see this similar shape here. So I'm going to be talking in the next handful of slides an awful lot about a fore-body shield and an aft-body shield. And all that means is the fore-body is the outer facing, the yellowish portion of this, and the aft-body is the underside of this. Between the two shielding designs is the soil sample is held. And so a cutaway of this fore-body looks more like this. It's a ceramic foam composite shield with a little bit of a graphite epoxy, a bit of a standoff, and then you have the fore-body thermal protection system layer right here. Whereas in the aft body, you just have a one layer or a one, without a standoff, a multi-layer aft body TPS design right here. So that's what I'm talking about by fore-body TPS and aft-body TPS. So we started here, we get kind of into this, and I'll use the laser pointer quite a bit. But we started by using SPHC to simulate 4 types of meteoritic and non-meteoritic debris impact materials that this craft could be impacted with in that time that it was orbiting and re-entering or on its way back to Earth. So we looked at simulations using dunite, which is a chondritic material, water ice, aluminum, and iron. We focused on likely obliquities, impact obliquities from 0 to 45 degrees, and impact speeds spanning 7 to 55 kilometers per second. In this area, kilometers per second is the velocity measure that we use. 7 kilometers per second is really the low end for many materials. Granted, it varies by material and by shielding recipe. But 7 is kind of on the lower end, but just starting to pass what we would call the hydrodynamic regime in shielding materials. 7 to 10 maybe. When you get into that hydrodynamic regime, all that means is the shock that's imparted into the shielding material. The damage is driven completely by the shock because the shock overcomes the material strength of that constitutive shield. So that's the big thing. You know, you're just getting different physics, you know, once you cross into the hydrodynamic regime compared to lower hypervelocity and ballistic velocities. That's the point there. So really, really fast velocities we're talking about here. This first, so some of you may or may not be able to see this. These plots here show, well, all of this shows the case of a 6.79 millimeter aluminum impact particle impacting the composite garage shield that I showed you. That's that conical structure over the four-body TPS at 25 kilometers per second and a 30-degree obliquity, a fairly common obliquity. And so this is a cutaway of that conical structure to reduce computational time, of course. This is the initial state. And the thing to take away in these region plots here, these three that I'm pointing to kind of in the left and in the middle, is that the aluminum pellet or the aluminum impactor that you see is identified by the blue material. And so there's the time steps are 0, 5, 10 microseconds and 30 microseconds. The legend colors in these region plots represent the materials modeled, while the colors in these phase plots right here represent an arbitrary scale from blue, which is a pure solid, to red, which is a pure gas. The important takeaway here is that the blue here is not the same as the blue in these. And if I get into why and what they mean, it's going to take an entire day. And so I just want to say, when you see the blue here, the information tells us is that here you can see the initial condition, the impactor going through the depth of that, the thickness of that outer garage shield. And then this really shows the breakup of the debris of that impactor and what it comprises in that debris, that resultant debris shield. This little rainbow thing, there's no significance between the colors here and there. I'm just telling you that this is the TPS underneath the four-body garage shield, and so is this. But this is the phase plot. What we can tell from the phase plots here are, it's hard for me to see here, but there's a variety of colors from blue, yellow, green, and red. But most of this debris cloud, it's a mixture of mostly liquid and gaseous particles. And what this SPHC, the simulations can tell us is that we know that most of the damage is actually coming from the liquid and the gaseous particles. The only other thing I want to say here is that the blue aluminum particles here, when you look at the phase version of this very same time step, you can see most of the blue aluminum particles, once they've traversed the thickness of that shield, are in a gaseous or a liquid state. So that's all we're seeing here. If you have better vision than me, you're going to see some dark blue areas here, which indicate damaged areas of that TPS layer. You're going to see light blue areas, which indicate compressed, highly compressed layers. And then you're going to see white void areas. And those are what we measured very carefully to be the penetration depths that you are going to see in the tables on the next slide. So we conducted these, measured the white areas, and looked at the deepest penetration depth and recorded what the deepest one is here. And so these tables are for all of these runs, for all these diameters and velocities. This is all 30 degrees for 7 to 55 kilometers per second. These are all the recorded, the deepest penetration depths that we could see in that TPS layer. So what does that mean? Like Williamson's earlier work, like the previous work here for the dual wall shields, we know in the discipline of hypervelocity impact that energy is a driver of damage. And so we just simply wanted to plot the maximum TPS depth versus energy. And how did we get the energy? We used the SPHC input parameters to compute the energy. And again, we plotted those versus on the y-axis versus the maximum measured TPS damage in those simulations. And this is what we got. So we find that the consistent with the earlier analysis, whether it's dual walled or sandwich shield, the higher penetrator impact energies, as you go to the right, leads to deeper TPS penetration at a given velocity or for a given material. and also that the penetration depths are greater for the denser materials. So iron and aluminum will penetrate deeper than, say, water ice. Pardon me, aluminum is one of the two softer. Iron and dunite will create deeper penetrations than water ice and aluminum. Here, you're seeing the very same plots I showed you on the previous slide. But what was a little bit novel is we expanded the approach from Williamson's previous work, and we wanted to understand, now that we had a garage shield covering, so different shield, covering that TPS and no longer dual aluminum plates, we wanted to understand what the contribution of that garage shield was towards the impact energy. And the way to do that most simply was by devising a term that we consider to be the overmatch energy. And overmatch energy is nothing more than that initial impact energy that's plotted here minus a ballistic limit energy. And ballistic limit energies were actually derived based on this very SPHC data. It's usually an empirical derivation. But a colleague of mine who wrote a different paper computed the ballistic limit equations and values for these very materials at these velocities and obliquities. And I use the ballistic limit term. And so what does impact minus ballistic energy mean? That just means what residual energy exists after the impactors go through that first shield, after they overcome the ballistic limit of the shield. What's that residual energy left over? We wanted to see if plotting versus just the impact energy versus plotting versus an overmatch energy gave us any differences in our results. And so what we really found was that the trend lines for either energy case were consistent. So the plots collectively illustrate that for a given penetrator material, the higher impact energies lead to deeper TPS penetration. And however, what was a little bit different is when comparing the plots of the lower velocities, so say the 7 versus 25 compared to the 55 kilometers per second, we noted that the denser particles, which if you can see, purple is iron in here. So the purple iron and the black dunite are more difficult to break up, and vaporization occurs at higher velocities where you don't see it at the lower velocities, such that the slopes collapse or close in on each other. You see this here. And so as opposed to these lower velocities. So you can really see a different physical phenomenon happening. That's just what that's showing. In contrast, the lower density particles, the blue ice and the yellow aluminum, are more easily vaporized, and they show less penetration into the TPS layer at a given impact energy. So there's no rocket science here, really. It's just a simple analysis of a couple of different expressions. And I am getting to the end here. But remember I said we had two shields. We had the four-body shield over TPS, and we had that aft body shield. And we wanted to look at the aft body portion of that shield as well. And what you see here are SPH simulations of two similar but different particle sizes. One's 1.25 millimeters and one's 1.55. This is strictly showing you what the particles look like as it's traversing the thickness of the aft body TPS, which is more of a honeycomb structure. And the impact obliquity for both of these and the velocity is 30 and 25 kilometers per second respectively. And again, for this type of the plot, the region plot, the blue areas illustrate the solid aluminum particles that are generated within the cloud. We also, for studies like this, wanted to understand what the ballistic limit curves were. So we derived these from the SPH simulations and those tables that you saw a couple of slides ago, where they decreased in value. And as soon as they got to a zero penetration, that's where we drew the points for the ballistic limit. There was no more penetration. And we we plotted those, and all this is telling us, this is a plot of the diameter of the sphere versus velocity. That's typical ballistic limit curve. All this is saying that the ballistic limit increases at higher impact obliquities, which we know for most shielding materials is the case. We're bringing this home now. We've showed in another set of studies that SPHC is an adequate and a convenient and actually a very good tool for helping us to model meteoritic and non-meteoritic materials into complex space shielding structures at up to very high orbital debris, which is more of a natural debris versus man-made debris velocities. And that this is a tool that we can use to look at complex types of shielding that are that are very complex geometrical structures, such as beneath these garage shielding enclosures. For body findings, as I already said, the maximum crater depth beneath that garage shield correlates with total particle impact energy. You saw there were linear relationships. Granted, the slopes were different. The penetration depth increases with impact energy. The slopes were increasing, sure. And that we saw when we looked at the color of each line, the denser particles cause greater damage than the lower density particles for a given velocity. Aft body, not as exciting, but it confirmed what we expected, that the ballistic limit increases for that simpler aft body structure as we increased impact obliquities. And so what's the so what? This work wasn't for naught. It did in fact result in an augmented TPS shield design for an enhanced ballistic protection against these interplanetary threats, and so we may well be using this in a follow-on campaign, but we are waiting to see what NASA decides to do. And many thanks to our NASA Engineering Safety Center sponsor. This was also a joint effort between multiple NASA centers and our ESA colleagues. So thank you. Yes.
I just have a question. How are you looking at model results here? What actually happens in space? How does that work?
Great question. There was a whole, this presentation could easily be an hour or two. So this model was validated many times. It's used in many different applications. For this particular study, we validated it against a whole lot of hypervelocity impact data that was obtained through a two-stage high velocity light gas gun at the University of Denver University of Dayton Research Institute in Ohio. Hundreds and hundreds of comparison data points. This was also compared against other similar national lab codes, ALE, if you're familiar, and CTH is another one that's out of Sandia. And so there was a fair amount of validation between, and where am I here? I have, oh shoot, hi Joel, did I get rid of this? I have some backup materials that do show, I think, some of those validation studies, because there were some, here we go, right here. Oh, the sharing has stopped, okay. Oh dear, what just happened? Can you see this right here in this room? So here are some of those SPHC predictions compared against the hypervelocity impact into the mesh structure. And you can see, a whole lot of time was spent on, SPHC makes these fingers, and we see kind of this tunneling in between the toes of the material. So yeah, there was very well validated. You had a question, yes?
Yes, potentially a two-part question.
Sure.
So I'm curious if you can speak a little bit to how the max penetration depth is used in the probability calculation I mentioned, and if that's easy to characterize, maybe short answer. Do you think there's anything to be gained by instead using a more stochastic representation of the damage? So, for instance, if you try to model a stochastic process, of how the damage is happening to that bottom part, instead of just looking at the max, so like a functional limit. So you try to get a more holistic characterization that would have an interesting impact on that probability calculation.
Okay, I may need to talk to you on the side because SPHC, and I'm looking at Joel here, but he's gone.
I'm here.
This would be perfect. This would be a non-stochastic answer. My understanding, SPHC would give us a deterministic result each time for a given set of conditions. I'm not sure what you were talking about using a probabilistic next time versus a, but did you?
We have a, maybe I can jump in here to
Sure.
Brooke. The key is that it's a highly stochastic process being hit by a meteoroid. There's a probability associated with the directionality, their sizes, their velocities. And so all of this work dumped into a code, which essentially drew random numbers and drew the flux that was coming into the spacecraft. And there is uncertainty associated with the particle impacts themselves. So we would compute the uncertainty with that probability of loss, which averaged around 1 in 500,000 for the 5-year mission. And so that's how we snuck in that probability or stochasticity. That wasn't in the impact side. However, we did have some uncertainty in actual differences between the predictions that we got from SPHC and real test data. A test will never come out exactly the same way every time. So we would place into the computation for probability of loss some uncertainty that had to do with test data. And we threw an artificial uncertainty into the SPHC predictions based on the uncertainties we would see in tests. So we did consider that, and if you'd like to talk about that offline, we'd love to talk more. I hope that answered the question.
Yes, thank you.
I'm glad Joel was here because that was a portion that he worked on that was not a problem. So thank you so much. Thank you. Now I understand what you're asking. Great. Do you want me to leave this? Okay, thank you, everyone.